Welcome to the topic of big data visualization. Today, I'm going to talk about some common strategies that we use to handle the big data problem. For scientific simulations, big data have become very common phenomenon. A lot of simulations, they're using high-resolution mesh and produce data that are much larger than what can be handled by a typical machine easily. So what are big data? Basically, big data can be a collection of data objects that the total amount is big, or each individual data object is large. For big data collection generated by scientific simulations, it can be aggregates of multiple data sets. For example, in a time-varying simulation, it will produce many time steps. It's possible that individual time step, the data set is small, but the collection of the entire simulation is large. Or the simulation will produce many variables, and this is the case of multivariate dataset. It is also possible that the dataset has many different sources. For big data object, we typically have a single object that is too big. For example, one single time step output of a simulation is larger than the local memory size, and it is too big to be read or write efficiently to local disk or remote disk. My following slides are mostly focused on big data object, that is, the object that is needed to generate some visualization is already too big for a typical machine. So what are the solutions for handling big data objects output from scientific simulations? One possibility is that both the visualization algorithms and the simulations are run in the same supercomputer. So the simulation will place data in the memory, and then you immediately run the visualization algorithm and produce geometry for rendering, and the output from the supercomputers are the images. Another solution is that the simulation is run in the supercomputer, and it will produce and send the data through a fast network and to a server that has large disk space. After that, the visualization algorithms are run as a post-processing in a machine that has a large amount of memory and the disk space, and it will produce geometry and render the geometry using the server. Yet another solution is we subdivide the whole pipeline into 3 tiers. The supercomputer will run the simulations, and then the data and some more expensive visualization is going to be run in a big server. On the client side, that is where the users can query appropriate data from the server to perform data reduction, and also it can perform local rendering to get interactive frame rate and analyzing the result. All the 3 options are possible, and which one you choose depends on the available environment. Sometimes if you don't have fast network and also you don't have big server available, you might be forced to run the visualization algorithm in the same supercomputer that the simulation is using. If you want to have interactive control as opposed to only viewing the images, you might want to use the 3 tiers paradigm. That is, store some data or even visualization output in the big server, but you leave the options of perform further data reduction on the client machine. So from the user point of view, you can query what is needed and perform interactive manipulation for further data analysis. In addition to the hardware infrastructure that can be used to run big data visualization, let's look at software analytics pipeline for scientific data sets. So starting from simulation, assuming the data is very large for us to look at its entirety. So what we can do is, first of all, we look at the data and we identify the existing features and also the locations that contain important features. Based on the features, we can go back to the data and select more important portion of the data, or we can reduce the resolution for the data that are not considered important. And this is so-called level of detailed data selection. From the feature, we can describe the data, which can be represented as higher dimensional vectors. And those higher dimensional vectors may be difficult to visualize to allow user to select more interesting data. So we will typically need to run through dimensionality reduction techniques. For example, multi-dimensional scaling or MDS. And those simplified feature vector, we can feed that into a machine learning process to determine what features are more important, and then determine what data in the entire domain are more important. The information we extracted from the data, the features, the feature vectors, the machine learning classification result can be fed to the visualization front end. The user can make a decision based on all the information provided and back to select interesting data from the original data sets and perform visualization and analysis. and this will become an iterative process. In the visualization pipeline I just described, data reduction plays an important role that allows us to handle very large-scale data set. The goal of data reduction is to reduce the memory, disk, and also network requirement when we perform visualization and data analysis. One particular thing to keep in mind is that we want to utilize the deep memory hierarchy shown in the triangle here, starting from the very base layer, remote disk or cloud, because it is more expensive to transfer data. We want to select useful data and then propagate them to faster but smaller memory. So what's the strategy to reduce the data as we move up to this chain of memory hierarchy? We can perform data compression. This can be done either in the remote or local disk. We can perform multi-resolution. So this is basically we only bring in and visualize high-resolution data in the local memory if they are important. And also we can perform data partitioning because if we break the data into pieces, it's much easier for us to move only the important data around. About what data to retrieve and analyze, a lot of times it's based on the query. So we can perform demand or query-driven visualization and data analysis scheme to further reduce the amount of data we need to touch. A lot of algorithms have the sparse traversal property. That is, in order to produce the visualization output, you do not need to touch every single data element. So when you implement algorithms that handle large data, you need to make sure that you utilize this sparse traversal property. And also, once data are brought into memory or faster caches, you want to make sure that you have good data access locality. That is, you want to reorganize your computational order such that the data can be utilized as much as possible. Other strategies for data reduction is to perform feature extraction. This typically requires domain-specific algorithms because features are different according to different applications. When the data are still too big to process, you can use parallel processing. That is, break the data into pieces and then divide that into different processors or threads to perform computation in a concurrent way. About breaking data into pieces, you might wonder, how come we cannot rely on the virtual memory scheme available in most of the operating system so that we don't have to perform any data breaking by ourselves? This is typically because when data is too large, if the data is not stored in an access-friendly format, for example, in the image on the left, data in a three-dimensional array are stored in a flat, slice-by-slice manner. If you need to perform operations such as volume rendering, you need individual small cubes. The virtual memory scheme is going to bring in the entire slice, access a few data points, and then you need to bring in another slice, but due to the lack of memory, he has to kick out certain pages to make room for the next slice, but you only need a few numbers from the next slice. Then you need to kick some data out to bring the next slice, and so on and so forth. You are going to experience very undesired thrashing problem. That is, you need to bring in and bring out large amount of data, but you only access a small piece out of them. To overcome this problem, typically it is best that you perform data partitioning by yourself. You reorganize your data into small cubes and then store it into the file, and this will allow you to perform much more efficient data access. When you perform data partitioning and the layout by yourself, there's one thing you need to be careful. That is, when different algorithms have different data access patterns, you cannot afford to perform data partitioning in a way that is too algorithm specific. That is, you don't want to create one file or one memory layout just for one particular algorithm. It is better to design a much more general data partitioning and layout algorithm that can be used by all the algorithms for the best average performance. Fortunately, most of the visualization algorithms have very similar local data access pattern. In particular, if you break your data into small chunks and organize those chunks in a certain manner, your algorithm can typically perform much more efficiently. Breaking the algorithm has a few advantages. For example, it will allow fast block retrieval. And also, you can design the algorithm in a way that you can prefetch blocks in parallel with visualization computation by performing smart prefetching. Now let's talk about query-driven visualization. As I indicated earlier, users are often interested in a particular portion of the dataset. So you might want to separate out data that is scientifically interesting and only bring in those data while you are performing visualization. And the premises of this method is that we assume the data subset of interest is much smaller than the entire data set. For example, you can perform a range query, assuming you're only interested in the region that have temperature lies in between 1000 and 1500 Fahrenheit degree, and you bring in only the data that satisfy this condition. So the focus of a query-driven visualization is a high-performance indexing scheme and a query method. Using the example of temperature here, how can you quickly identify data points that have temperature falls into the range that you're interested in without going through every data element to search? Also, you want to design efficient query specification interface so that user can understand the distribution of data so that they can formulate better queries. This slide gives you one example of how people support fast indexing for query-driven visualization. And this is done through bitmap indexing scheme. Assuming you have two-dimensional data set, among those data points, you have a minimal and maximum range. What you can do is you can divide the range into a few intervals. In the example here, we divide the data range into 7 intervals. And then you can create a bitmap indexing. What is that? That is, for every data element represented as a row, we store which interval the value of this data element falls in. For example, the first row represents the first grid point. I have a grid ID 0, and then I store a bit string, indicates that the value of the first point falls into only the first bin. The other bits are 0 because the value for the first data point are outside of those intervals. And this I column indicates which bin the value of the first data point falls in. The second row again is the second data element, and assuming its value is in the range of first bin. So I only make the second bit 1 and the other 0. This indicates the value range that the first data point falls in. Similarly, for other data elements, the second, third, the fourth, and so on, each data element we represent as a row of bits. Essentially, this is a quantization scheme, and also we use bitstring to represent which interval the value of data record falls in. This allows us to do fast query. For example, suppose I want to find out all the data elements whose value falls into the third bin. We can scan the column that corresponding to bin number 3, and then we can skip those data elements that have value 0 and only focus on the elements that have value 1 in the bit. This will allow us to perform a quick retrieval. Another advantage of using bitmap index is you are going to see a large number 0. So people have proposed different long length encoding scheme to compress this bitstream. This will allow us to represent the data in a much more compact manner. About sparse traversal, as I indicated, we want to utilize the memory hierarchy as much as possible. And then memory hierarchy, in particular, the small but fast memory can be better utilized if your algorithm does not need to scan the entire dataset. Instead, you only focus on a small sparse set of data when we perform computation. So when you design an algorithm, you want to make sure that you touch data as little as possible. You do not traverse data unnecessarily, and this is why we call that sparse traversal. In the example isosurface extraction, you do not want to touch regions that don't have minimal and maximum value contain the ISO value. When we perform particle tracing for visualization, you do not bring in data element that the particle does not have any hope to enter. For volume rendering, as you are performing ray casting, you are casting the ray according to your current ray direction, and a ray is going to touch only a small number of blocks, and you should design your algorithm to make the computation more efficient. Oftentimes, if you want to ensure sparse traversal, you need to somewhat modify your algorithm and be very conscious about what data is needed and how can you make the best use of data that you are going to retrieve. And there's a category of algorithm called audible core algorithm. The goal is exactly that how can you perform a computation that requires a large data set efficiently by touching and then limit your computation to local regions. And finally, when all the strategies I mentioned above have been used, but still the dataset is overwhelmingly large, then you can resort to parallel computation. The reason we want to use parallel computation is that the amount of aggregate memory in a supercomputer is often very large. Take the Blue Waters machine as an example. It is a Cray machine that has mix of XE and XK cabinets. In the XE node, it has 64 GB memory per node, and with the 22,640 nodes, we have a total of 1.38 petabyte of memory that you can load the data and perform in-core computation. Blue Waters also contain XK node. In each node, we have 32 GB memory, and it also has GPU memory that is 6 GB. And among all the 4,224 nodes, you have 135 terabyte memory available for you to perform in-core computation. And also, you have 25 terabyte of memory in the GPUs that you can perform highly concurrent computation. Okay, so this concludes the overview of big data analysis and visualization.